Hello everyone. My name is Jong-hyuk Park from Hankuk University of Foreign Studies, and this work was done in collaboration with Seongkyungkwan University and Samsung. Today, I'm gonna present FlashAlloc, dedicating flash blocks by object. In this work, we propose a novel interface for flash storage called FlashAlloc. This allows users to pass logical address ranges of objects to the flash devices, which enables stream writes by object. So let me start the background. Most data stores handles data by logical object. For example, SS table in RocksDB, double light buffer in MySQL, and segments in F2FS file system. Host-side application aware object as unit of logical space allocation and clusters data by calling fallocate system call. Unfortunately, the storage has no way of knowing the logical allocation information of the object because it simply follows the stream writes by time policy. Also, when an object is overwritten or discarded by stream, all its data pages tend to be invalidated together at once, having the same death time. However, flash blocks are multiplexed with pages with different death times. This incurs huge write amplification. With stream writes by time policy, flash device will pack those writes in their arrival order into flash blocks. Since logical objects have different death time each other in most cases, pages in a multiplex flash block will be invalidated at different points of time. We call this as a multiplexing. When the block is chosen as a victim for garbage collection, the remaining valid pages have to be relocated to another block. This amplifies the physical write. So, the root cause of multiplexing is that flash devices are object oblivious. That is, host semantics about the object's logical address range cannot cross the storage interface wall. With this problem in mind, we also observed that data stores with flash-friendly write pattern might not align our common belief and can actually experience write amplification. These are our motivating experiment results about write amplification in flash-friendly data stores, especially for RocksDB tenants with pre-random workloads suffered from the high write amplification. Though each SS table file is sequentially written, multiple compaction threads will flush their SS tables concurrently, and write requests are split due to the file system fragmentation and I/O scheduling. According to the stream writes by time policy, multiple SSD files interleave at the flash storage. As a result, pages from multiple SS tables with distinct death time tend to be stored together in the same flash blocks. To tackle this problem, there are existing solutions controlling the physical placement of write inside flash storage, multi-stream SSD, and GNS. First, multi-stream SSD allows applications to place pages with different write times to different streams. However, the static binding of limited stream IDs raises several issues. Especially, write streaming effects are diminishing due to the stream ID confliction in multi-tenancy. Also, there is no stream-aware garbage collection, so eventually, pages with different stream IDs are stored into the same flash blocks. As a result, multi-stream SSD still suffers from write amplification. And GNS is recently proposed, which exposed the zones to host as the unit of data management. However, this imposes strict sequential write ordering rule, which is hard to adopt in existing data stores. GNS avoids block interface tags, but this introduces yet more expensive log structure write taxes in terms of logical write amplification. To solve this multiplexing problem, we propose a flash alloc interface that enlightens flash devices to streamline by object. This approves the host semantic about object LBA range to storage device. And thus, it demultiplexes objects with distinct death time into per object dedicated blocks. Even logically fragmented objects can be physically defragmented into the same flash blocks. In a nutshell, flash alloc enables per object fine-grained write storing. Flash alloc requires minimal changes on application and FTL, and there is no need for additional translation layer or mapping information in host side. Flash alloc is best suited for application that manage logical objects with distinct death times, or those that are sequentially appended and cyclically reused. However, flash alloc is neither for small and random overwrites, tiny objects, and append-only writes of uncertain sizes. For such cases, we recommend executing a normal write without invoking flash alloc command. A host application can pass the object's logical allocation range to storage using the flash alloc command. Upon receiving a flash alloc command, the flash storage creates its corresponding flash alloc instance. It then secures one or more entirely clean flash blocks to separate the writes specific to that instance into those dedicated blocks. When multiple blocks are allocated for an instance, the data corresponding to that instance will be striped across the channel to enhance the bandwidth. Next, core operations. For a write request, it first probes the matching flash alloc instance using LBA ranges. If there is a match, the data is appended to the block allocated by flash alloc command as pointed by the next write pointer. Subsequently, this pointer and logical to physical mapping tables are updated. If there is no match, then the operation proceeds just like in a conventional SSD. The data is stored into the normal block. The read operation is executed in the same manner as a conventional SSD. Lastly, flash alloc enables achieving nearly zero overhead trim command. This is because pages in a flash alloc block have the same death time. This means that this command can be completed by erasing entire block instead of invalidating individual pages. With clustering pages with same death time into the same flash block, when the flash alloc block is selected for victim in garbage collection, there is no copyback. Since new flash alloc block must be secured to total clean block, so it is available from free block pool or merging multiple blocks to secure clean block. For this, we introduced the garbage collection by block type scheme. While selecting victim blocks, flash alloc makes the pages from normal blocks are not mixed with the flash alloc block. So this scheme adaptively allocates space depending on victim block type, flash alloc block, and normal block. We prototype the flash alloc on Real Cosmos plus OpenSSD board. To evaluate the performance benefit of flash alloc on key value store, relational database, log structure file system, and multi-tenancy. We measure the throughput and WAF while running two benchmarks, DBbench and TPCC. All experiments are conducted until the storage device becomes full. In both RocksDB and F2FS file system, FlashUnlock constantly delivers a nearly ideal WAF and higher throughput than the vanilla version. In vanilla RocksDB, SS tables populated by multiple compaction threads concurrently, they are multiflexed into the same flash block. Recall that SS tables at different levels will be compacted and thus invalidate at different points of time. This leads to high write amplification. However, FlashUnlock significantly reduces write amplification by separating SS tables into distinct flash blocks. In vanilla F2FS, concurrent log writes from active segments are multiplexed into the same flash block. On the other hand, we utilize FlashUnlock whenever a new segment is allocated, and thus each segment's writes are isolated in its dedicated flash block. We'd like to note that FlashUnlock can also be a fundamental solution for log-on-log problem. Next, in MySQL, double-live buffer is used for guaranteeing their atomicity. Before flushing Dirt pages to their original locations, MySQL sequentially appends write to double-live buffer, which occupies a continuous logical address space. Therefore, we separate double-live buffer in MySQL, which has cyclic and sequential write from main databases. Given that the writes to the double-live buffer account for nearly half of the primary write volume, we observe that using FlashUnlock to isolate objects proves beneficial, even with the intervention of normal write. Additionally, for multi-tenancy case, where the RocksDB and MySQL instance run together, we found that FlashUnlock makes tenants more altruistic to neighbor tenants. Lastly, we also conducted a comparison with the multi-stream SSD. For this, we prototyped the multi-stream SSD using the same Cosmos Plus Open SSD, which supports 8 streams like commercial multi-stream SSD. More importantly, when the number of SSD files exceeds the total number of stream IDs, each stream has to be shared by multiple SS tables with varying write times. Furthermore, there is an absence of stream-aware garbage collection. That is, pages with different write time streams are mixed in the same flash blocks. As a result, multi-stream SSD still suffers from write amplification and is more worsened in multi-tenancy. However, FlashUnlock offers a fine-grained allocation with a garbage collection by block type scheme. Therefore, this effectively eliminates the write amplification. In summary, we present the FlashUnlock, which enables per-object fine-grained write streaming. We believe that this is the great alternative to existing solutions such as multi-stream SSD and GNS. FlashUnlock not only reduces WAF, but also improves throughput. Furthermore, it is beneficial in multi-tenancy as it mitigates WAF interference among multiple tenants. Thank you for listening, and please check out our paper and code. In the paper, we delve into the details of implementation and more experiments, which further explain our design principles. If you have any questions, please don't hesitate to reach out. Thank you.